laser pointer, right? Yes.
Just a sec.
Are we going live now?
Not, yeah, I can see your laser pointer. Well, I think we should wait because I don't see any audience.
Okay.
Probably people are busy watching Spider-Man.
Yes. Yeah, yes, you can. Yes, I don't see any audience. Though I think at some point we should just go ahead and, do it, and it just remains on YouTube and people will watch it there.
Okay.
This is very, very crazy. There has been some communication failure somehow. I don't know what.
Yeah.
Okay. Okay, I get it.
Okay, go live. I think we are live somehow. Just go live. Yeah, we are live.
Okay.
I'm going to start. Manisha, are you live?
Yeah, wait a minute. I need to give the description about the thing which I didn't give it.
Just ignore it and go live.
Okay. Start live.
Okay, a very good morning to you on Sunday, the mid-Sunday of the month, which means it's time for Chai and Why. We continue with our series in December that look at the work done related to the Nobel Prizes for the year. And today we're going to be looking at part of the Nobel Prize in Physics that was given this year to Giorgio Parisi for his work on complex systems. And to tell us about that is going to be Saranyo Moitra. But before that, let me tell you that we will be having a special Chai and Why session next Sunday as well, where we will cover the other part of the Physics Prize as well as the Chemistry Prize of the year. And hopefully, we do have permission that from 2022 January, Jan 2nd, our first session at Prithvi Theatre, we should be able to offer in-person experience of Chai and Why again with the chai. That means, though we are still hoping that everything goes well with the Omicron regulations, but we hope that we will be live at Prithvi Theatre on January 2nd as well. But for today, it's going to be an online session on the Nobel Prizes of the year, the Physics Nobel Prize. And remember that we really can't see you, so please give us your comments via the chat. If you're watching us on YouTube or Facebook or in the Zoom session, please feel free to put in your questions and comments by chat. Thank you. So with that, it's going to be over to Saranyo for today's Chai and Why. Saranyo is a research scholar in the Department of Theoretical Physics at TIFR with interests in all kinds of things. And he's going to tell us about the world of the complex systems and take us through order and disorder today. So over to you.
Right. Thank you, Arnab, for the nice introduction. So today I'll be trying to do whatever job I can of Giorgio Parisi's work, which won him the Nobel, part of the Nobel in 2021. So this year's Nobel Prize was awarded to Syukuro Manabe, Klaus Hasselmann, and Giorgio Parisi for groundbreaking contributions to our understanding of complex systems. The citations read for Giorgio Parisi as for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales, whereas for Syukuro Manabe and Klaus Hasselmann, it states for physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming. More on this part, as Arnab mentioned, from Divya on 26th of December. Today, we'll be focusing on Giorgio Parisi. Now, before we go into his works, let us talk about Giorgio Parisi, the person. So he was born on 4th of August, 1948 in Rome, Italy. He did his bachelor's, master's, and also his PhD with Nicola Cabibo at Sapienza University in Rome. He graduated in 1970. And he has moved around in Europe and in the USA afterwards. And since 1992, he has been a full professor of theoretical physics at La Sapienza. And very recently, he also got conferred the Nobel Prize in physics. Now, this is only the newest feather in his cap. This is also right after the Nobel announcement on 5th of October, hot on the heels of the Euro Cup finals, where the Nobel Prize also came to Rome. And this is on the 6th of December when Professor Parisi was awarded the medal in La Sapienza itself, right at the place where he started his entire physics career. As I said, this is not the only award he has received. He has received many, many more, as you can see from this pretty illustrious table over here. But despite all of these, most people know him as a very gentle person to talk to. He's very kind, and he always makes people feel warm and welcome during any scientific conversation. Now, he's also a very active person a very vocal person about science funding. He's been leading the Salviamo la ricerca italiana movement since 2016, which is basically a drive from Italian and international researchers to push the Italian government to fund research in basic sciences above the subsistence level. So it was sent as a letter, a petition on Nature with 69 other signatories. And it's also interesting to mention that he has used the current attention that the Nobel Prize has garnered him to highlight these issues in whatever platform he could. So they also make really satirical comics. So I can offer you a translation where one person is asking, how is the research going? Whereas the other person basically says, we find everything except money. So Giorgio Parisi has always mentioned, for example, in his conversation with Adam Smith on the Nobel website, that it's important that people who in the end pay the bill for science have some understanding of what science is going on. He also mentions during his acceptance speech that he hopes that his Nobel will now be useful for Italy to underline the importance of science in our country. And this is not something limited to Italy. It is true in India as well, and most of the places around the globe where basic science funding is not treated with due respect. And the debate on this is large and broad, so I'll keep it at that and move on to Giorgio Parisi, the scientist. He's a prolific researcher with a career spanning more than 50 years. Remember, he graduated in 1970, and he's been publishing till then, and he's still active in the field. His most recent paper was just 24th November, so less than a month ago. Now, he has worked on a diverse set of fields and diverse set of problems. And on choosing research problems, he had to say that his mentor, Nicola Cabibo, was usually saying that we should work on a problem only if work on that problem is fun. Now, of course, he adds on top of that that fun is very vague and you don't really know how to quantify that. But he clarifies that anything that you find interesting and you have a strong conviction that it is something interesting is worth working upon. And as a result, he has worked on a wide range of topics, as I mentioned, starting from quantum chromodynamics, spin glasses, intermittency in turbulence, bird flocking, and many, many more. Now, to give you an example of things he finds fun, there's this paper from 2007 on conference registrations, how people react to a deadline. Now, what they find over there, or what they do over there, is that they had two conferences, Stat Physics 23 and some other conference, which was also happening in Italy. So they took the number of registrations as per day, and they plotted the total number of registrations as a function of time. So N of t is the total number of registrations, t is the number of days, t star is the deadline for registering on the conference. And they see that all of this data from two different conferences, Stat Physics 23 being the red triangles over here, and the other conference being these blue dots over here, miraculously fall on the same curve. And actually, they take a very simplistic model where they say that the pressure to register is inversely proportional to the time left before the deadline, which makes sense, right? The closer you are to the deadline, the more pressed you are to actually register or submit something. So they take this simple phenomenological model, and from that, they actually get this black trace over here, which falls upon the data itself. As in, it is fitted to the data and you get a good fit. So what they basically model it as, T star, as I said, is the deadline. The probability of registering is inversely proportional to the distance from the deadline, so T minus T star. C is some proportionality constant. And they find that the total number goes as logarithmically in this fashion. So there is a logarithmic divergence at T star. What is the takeaway from all of this? Procrastination is universal in the literal physical sense as well. Now, moving on, and I find this a really neat piece of work. I mean, it's nothing difficult. It is nothing complicated per se. Just applying things that people routinely use in his field to things which almost all of us face in this world. Now, let us take a look at Giorgio Parisi's Google Scholar profile, and this will give us a little snapshot into how prolific his work actually is. So as you can see that he's a highly cited author. He has very diverse interests, and he's been acting since 1977. Now, one thing and we should note over here is the fact that the range of things that he has worked in. So for example, the first one, asymptotic freedom in parton language, is from subatomic physics, particularly quantum chromodynamics. Spin glass theory is, of course, from disordered systems, a field that he was one of the generators of. Dynamic scaling of growing interfaces is a very famous paper. It's basically related to statistical mechanics. Planar diagrams, of course, is more from hardcore quantum field theory. It's a more mathematical paper. Simulated tempering is basically about novel numerical techniques to simulate spin glasses and so on and so forth. Whereas this interaction ruling animal collective behavior, as the name suggests, is from animal behavior. So as you can see, there is a vast difference, vast array of scales even that this person has worked on, and vast levels of complexity that he has tried to answer during his work, and has made substantial contributions and substantial effect on the field of each one. Now, of course, within a 1 hour period, it is impossible to cover all of this. So what we will try to focus on is what he got, is the field in which he got conferred the Nobel Prize, which is complex systems. So since I mentioned about scales, let me flash that particular thing as well. In fact, the selection of what I will flash is slightly guided by what I find to be cool rather than what I find to be scientifically rigorous or scientifically heavy. So if I omit some of your favorite works from Parisi's repertoire, please excuse me. Now, let's talk about scales. The human being is roughly, so this is a logarithmic scale of sizes. So on the right, it is increasing. On the left, it is decreasing. In the middle, conveniently or anthropocentrically, we place ourselves, human beings, who are roughly at the scale of 1 meter, 1 to 2 meters, whichever. That's the scale of us. If you fast forward to 10 to the power 10 meters, you get the scale of the planet. If you fast forward 10 orders of or 11 orders of magnitude even more. Remember, I'm talking about orders of magnitude. So this is quite huge. So if I go to orders of magnitude, there's the Milky Way at 10 to the power 21 meter. And even further is 10 to the power 26 meters, which is the size of the observable universe as we know. On the other side, if we go down to microns, 10 to the power minus 6 meter, we have cells. If we go down further, 10 to the power minus 10, we get atoms. Even further down, if we have nuclei, and way down 10 to the power minus 35 is the Planck scale, beyond which whatever we know about theory, we don't really know anything anymore. Beyond that point. Of course, ironically, this scale is not 2 scale. So this one should be much further down, but then for illustrative purposes, this is as it is. Now, so where does are the disciplines that we know of, the basic science disciplines that we know of, where do they reside? So suppose I want to talk about biology. Biology would work somewhere in this range over here. I hope you can see my annotations. Arnav, can you confirm that you see my annotations? Okay.
Yes, we can see your annotations. Yes.
Great, thank you. So chemistry, on the other hand, would work somewhere over here. Of course, these are rough scales. There's something called exobiology as well. So I'm just doing some rough scales over here. So chemistry would roughly be over here. Just to give you an idea of what's in between the scales, you would have, for example, you would have oceans somewhere over here. Climate also, the atmosphere would also be roughly at this scale. Whereas you would find, for example, birds or other things somewhere over here. Remember, these are very, very heuristic. You would find, for example, RNA or DNA somewhere over here. And so on and so forth. So you can make a gradation of where what is. Now, chemistry is over here. Now, if I were to actually now annotate where physics would lie, there's physics to be found across all of these scales, which is in itself something spectacular. Of course, very different kinds and very different disciplines of physics, but then you can still find physics across all of these scales, starting from the larger scales where cosmology is active to the smaller scales where people are trying to think about the fundamental forces, the fundamental nature of our universe itself. Now, where does Professor Parisi's work lie? So, as I said, he started from quantum chromodynamics, from high energy physics, which lies somewhere over here. And then over the years, he has gradually drifted towards here. So glasses, etc., materials would somewhat lie over here. They would lie somewhere over here. So here I would have glasses, or rather the microscopic constituents of glasses. Here I would have QCD. And over here, I would have things like climate. So Professor Parisi has worked on this entire range. Remember, this is 61 orders of magnitude between the left and the right. And he has worked on almost, at least in this very inaccurate scale, he has worked on a sizable fraction of that scale of magnitude. And as far as now, you might also ask, like, where do complex systems arise on this scale as well? So I'm running out of colors, so maybe let me choose another one. Complex systems roughly arise somewhere in this range. So true to the Nobel citation, it goes from atomic to planetary scales. So this is complex systems. So with that idea about scales, let us actually go back to what Professor Parisi has done. So I repeat the Nobel citation for Professor Parisi. So it's for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. We have already seen this entire thing about atomic to planetary scales. The two other ingredients that we need to talk about are disorder and fluctuations. So before I go into the actual physics behind these, or try to go behind the physics of this, let me actually show you what phenomena these things are actually talking about. So let me talk about fluctuations first. So suppose you have a situation where you have a random, you have a substrate on which you are depositing little boxes, little units. Everybody over here probably has seen or played or at least heard of Tetris. So think of it like a Tetris game where instead of having different shapes and sizes, you only have a unit box which is always falling down like this. Now for random deposition, if a box was coming from here, it would just stop over here and create a new box. If the box was coming from here, it would just fall down and create a box over here. So for each column, boxes are falling at random, identically and uncorrelatedly, and they would just go down to the lowest place possible for them in their column. The other model would be called ballistic deposition, in which case, if I start in the same place, instead of this thing going down all the way, whenever it encounters, the first time it encounters a neighbor, it gets stuck. So pictorially, this box over here would get fall down over here. This box would get stuck right over here. That's why you get all of these crazy looking structures over here. Now, what happens over time as well when one way is growing this way, the other ballistic deposition is growing in this way? What changes? So for random deposition, if you look at, so in this side is the horizontal coordinate over here. In this side, it's basically a height, which is also a proxy of time. More time passes, more the surface grows. So as you can see, every site is statistically the same as each other. So 30 with 40, more or less over time is the same. They have the same kind of fluctuations in time. Whereas for ballistic deposition, you can easily see that the landscape is much more complicated. It's qualitatively different, even in the level of a very simple computer simulation. You have these gaps where things just start sticking to one, and they have this propagating gaps in one direction, and so on and so forth. Now, well, why do I care about all of this? That's a very simple question one can ask, and it's a very legitimate question as well. The answer is that it's because examples of ballistic growth actually exist in nature. For example, you have frost formation. To give you an idea, let's look at this little video. So you have, let me sort of, right. So this video, which shows how frost is forming on some berries, which you can find at this link over here, over time. And as you can see, the frost actually forms in very corrugated ways, as if it's just growing in whatever place it can. So this is one example. There's another really cool example, which I recently found out about, called fluff fires. Now, fluff is basically some kind of debris that fall out of poplar trees in this case. So this is a place in Spain where they have a lot of poplar trees. And during the course of some months, these almost create a large carpet on top of the grass underneath. And the easiest way to get rid of all of this, instead of manually cleaning everything, is to set it on fire. So, for example, you can see this is a fluff fire in La Roya, Spain, where they set fire to the fluff to clean it out. It's very combustible, highly combustible. So the rate at which it burns doesn't really injure the grass or the trees. Of course, there's some debate around that, but this is another thing. So one can ask, with what distribution does the front of this fire pattern grow in time? Similarly, with what distribution does the front of this ice surface also grow in time? So these are valid questions to ask. And the answer is that it grows according to what is called the Kardar-Parisi-Zhang equation, now in literature, which was introduced in a 1986 PRL. So what I'm showing here is a plot of the height that is created, and this is the horizontal coordinate, as I told you earlier as well, and the color scale corresponds to the elapsed time. So you start at time equal to 0 with some initial condition, and then you let it grow with ballistic deposition. So this this is probably actual data which was collected from disordered liquid crystals. Now, the equation actually turns out to look like this. Don't worry, it's just, I'll explain what the math is. As I said, this H is the height field that you're seeing over here. Why do I call it a field? This height has a value at every point of space and at every point of time. So if I were to make a section through this, say at 40 seconds, so somewhere over here, I would get that at minus 1000 of X, it is this much, around slightly less than 1500. At around 0, it is like around 1500, and so on and so forth. So that is the height field. What this is saying is the time derivative of it. So how it grows in time is related to how it actually, so the second derivative of space of the height field. So, and it also has something called a nonlinearity. Remember, this is like the derivative of the height field to the second power. What that means is that it has two factors of the height field inside it. That's why it is nonlinear. And there's this new thing called xi over here, which is something, it's called, which encodes all the fluctuations in the problem. So what you have ultimately is a noise term xi, which depends on both space and time, and it has some statistical properties. So you have the correlators of psi being equal to some Gaussian amounts. What that means is they're delta correlated, meaning that they only influence each other at the same point of space and at the same point of time with some relative strength, 2D. And they don't have, on average, the fluctuations go to 0. So it's something which is fluctuating around 0, and it has some correlations. And just by putting in this fluctuating term and the nonlinearity, so I'm talking about the fluctuation piece and the nonlinear piece. If both of these are put together at the same time, they co-conspire to give this entire rich phenomenology of ballistic growth that we have seen over here. Remember that this is not something special. The KPZ actually has a fixed point over here. So which means that a lot of different kind of phenomena, for example, random tilings, traffic flow, random interface growth, which I was talking about, all of these have the same kind of physics at large length scales and large time scales. So this is something interesting in its own regard, because understanding this lets you actually understand multiple phenomena at the same time. Now, moving on. So all of these images were taken from Ivan Corving's website from Columbia University. Now, moving on, there's another really cool example, which I like to call dances in the sky. Let me try to play this. Just give me a moment. Yes. So as you can see, these are tiny birds called starlings, which are very common in North America and Europe, and across some parts of Central Asia as well, which are common to see in the evenings. They come out, they try to feed, and they move around in these mesmerizing patterns in the sky. And this is all done by themselves, all done in the sense of they self-organize into patterns like these and move around in such ways. So people would like to know what actually makes them, individual birds, come together in such fantastical ways. As you can see, each individual bird is just trying to fly for its own self. However, they can miraculously talk to each other over really large distances. So one single bird is something like this, and the scale of this swarm is probably 100, if not 200 times more than it. So they can actually communicate and give collective effects. So that is one of the themes of Professor Parisi's work as well, where we try to explain collective phenomena. Just give me one moment. Yes. So each bird has a local orientation, as you can imagine, and they follow a very simple rule that they update their orientation based on which direction their neighbors are going. Of course, it is dependent on, people have shown that it is dependent on their site and so on and so forth. Now, depending on how strong the tendency is to fit in with your neighbors, it can give rise to all of this nice flocking behavior. This is called flocking. So Professor Parisi has also worked in all of this, and he has made some contributions in all of that as well. Now, both this thing, which actually is on the 1 meter scale, and for example, glasses, and which is further beyond the 1 meter scale, and other examples as well. For example, the liquid crystals, which are on the sub-meter, micrometer almost scales, they all exhibit similar behavior, and they're also classified as complex systems. So let us talk about what complex systems are. Now, this is a pretty involved infographic, so I'll take you through step by step on it. So a complex system is something that has many components right here. So it has, a complex system like this has many components, each one component dynamically interacts with each other, and it is built out of tiny simple systems over here, and they're grouped into units. To give you an example, think of the human body. You know that human bodies are made of cells, and when you take a bunch of cells together, you create a piece of tissue. For example, if you group a lot of one particular type of cells together, you create muscles. You group together other kinds of cells together, you create the brain. You group another set of cells together, and over time they will form bone. And collectively, they're very different from each other, even though everything started from the same cell when the person was a fetus. And it all divided and differentiated over time to give rise to complex behavior. And as you can imagine, for human body as well, there is a lot of crosstalk between these levels as well. So that is what is being shown over here, that things are built out of composites. There is some self-organization, and there is some level of hierarchy to things as well. And as a result of this hierarchical structure, there is something which emerges out of the collective. So if, for example, I would like to know what happens for one cell, if I know everything that happens for one cell, I wouldn't be able to immediately say that, oh, well, this one, the bone will actually be something stiff and the muscle will be something elastic. Just by studying one undifferentiated cell, I wouldn't be able to say what happens to that. So this is a hallmark characteristic of what is emergent behavior, which only, as the name suggests, only emerges when you have a collective. So this is summarized over here. You have many components, you have mutual interactions between them, there is crosstalk across multiple scales, and there is an emergent behavior out of the collective. Now, in certain systems, there's also chaos, which means that fine changes in the little details in small scales actually influence very large scales. This is something that is very much present for the weather and for the climate, and this is one of the main results of Professor Klaus Hasselmann's work. Divya will cover that at some point. Now, let us talk about now emergent phenomena. Now, to give an example, like I gave before, think of the water molecule. The water molecule, suppose you know everything about a single water molecule, but that doesn't necessarily tell you that at a certain temperature, the water molecules will freeze in with each other in this particular form to give you ice. At some intermediate temperature from 0 to 100 degrees Celsius at not normal pressures, they will be partially ordered. They will give rise to what we know as water. And above 100 degrees Celsius, they will actually turn into steam. So this is something that only happens when you put a huge bunch of water molecules together and they interact between themselves to collectively give rise to these phenomena, or these emergent phenomena are also called phases. So this is the ice phase, this is the liquid phase, and this is the gaseous phase. Now, to know what is happening in the water, of course, I don't need to know how each atom or each molecule is behaving. I don't need to know whether this one is whizzing to the left, this one is whizzing to the right. I don't need to know any of that. All I need to know is how much volume it occupies, what is its temperature, maybe what is its density, maybe what's inside it, and that's it. I don't need to know details, microscopic details about things over here. So this is another trend. This is another conceptual shift that happened in physics at one point, where instead of trying to explain the fundamental, like say string theorists or high energy physicists try to do, you try to look at collective of many constituents and treat them in a statistical manner, meaning that you only care about averages and you only care about fluctuations around those averages. Now, since I talked about phase and it is controlled by temperature, you also get you also get something called a phase diagram, where below a certain temperature, you know that water will always be ice for any pressure that you give. There is this triple point, which is also the melting point in a sense, at some particular thing. There's the water phase over here, and there's the water vapor phase over here. This is, of course, out of scale. The actual phase diagram looks something like this in a realistic scale. Now, you have all of this. You have phases, you have emergent phenomena, and we talked about that these phases, this pressure and temperature can be linked to the microscopics through averages and statistical considerations. Now, the point is that how do we model emergence? So as I talked to you about, you have caricatured basic units. You need to capture the essence of the phenomenon. The details do not matter. As long as you capture the basic essence of it, the other details you can throw away. So you have some caricatured units. Then you have something called configurations. For example, a configuration of water molecules would be where each molecule is at one point on one snapshot of time. How are they moving? Which direction are they going? That's a configuration. There is some simple interaction between the units. As we saw before as well, there were some dotted lines between the water molecules. So there's some simple interaction between them. And there has to be some guiding principle to choose between configurations. So for most equilibrium physics, this is the energy minimization condition. To be precise, is the free energy minimization procedure. So what that means is that if you take a random assortment of all sorts of things, if you put them together, the system in equilibrium will try to go to the state or the configuration with the lowest energy possible, which makes sense, right? I mean, we're mostly lazy as well. Given some choice of convenience, we will go towards the most convenient option, which also means the option with least effort involved or least energy involved. So in a sense, this is a heuristic way of motivating what energy minimization is. To give you an example, let's talk about magnetism. So, so for example, for magnetism, in a sense, you can treat a magnetic material as composed of tiny little magnets inside, which either can point north or south by themselves. So think of them as tiny little arrows. Ideally, or more accurately, they're called spins. We don't have time to go into the actual details, but think of them as arrows. So for simplest studies of magnetism, you would consider a system with some lattice points, meaning you would consider a periodic arrangement of sites where these arrows can sit, and each arrow and each point can have an arrow either pointing up or pointing down. So the configurations correspond to different, so the caricatured basic units are the arrows, the configurations are strings of up and down things like this. For example, this is a configuration of 5 things, and then this is also a configuration of 5 arrows like this, 5 spins. There is some interaction between the units. In this case, there is some interaction which basically says that the spins like to align with each other, meaning that if, so there is something, so each spin has a variable called Si, I indexes each site over here. So interaction between the spins can be Si, Sj, which means that if both of them are +1, so Si, Sj, and there is some energy scale associated with it, J. So if I take independent values of Si, Sj, it can be say +1. So up I'm assigning as +1, down I'm assigning as -1. Both of them are +1, Si, Sj will be +1. If any of them are +1 and -1, they will be minus. Also for minus plus, they will be -1. And then minus minus also gives you a plus. So why am I doing all of this? It just tells me that one configuration is at energy, 2 configurations are at energy -j, and 2 configurations are at energy +j. So in a situation where you only have 2 arrows and you're looking at low temperatures, the configuration which is picked out is this one. This is the energy minimization procedure. Of course, in a realistic or rather in a more complicated model, you would have multiple of these SISJ terms sitting together, and depending on the sign of J, they can give you an ordered phase or a disordered phase. So what do I mean by order? For example, if the temperature is very, very low, meaning that you have very little energy in the system, it is seen that in such cases, things with the minimization procedure in place, everything tries to align with each other in a perfect way. When there's a lot of temperature in the system, means that each one has a lot of energy, which means they can flip around and do a lot of things. They have, so this is low temperature, which is also called ordered. And then there is high temperature, where you have spins which are misaligned with each other in random ways. So this is high temperature or disordered phase. And then there is a transition between the 2 phases, and that gives to phase transitions and so on and so forth. Now, in fact, this is not the entire story, because here I had said that all of the units interact with each other in the same way. Turns out this is not the case for glassy systems. It actually happens that you get some phenomena called frustration. So to quote Parisi himself, it's studying spin glass is like watching the human tragedies of Shakespeare's plays. If you want to make friends with 2 people at the same time, but they hate each other, it can be frustrating. What it means is, suppose I have 3 spins together, 2 of them want to anti-align. The third one also wants to anti-align with them, but then if it anti-aligns with this one, it aligns with the other one, which means that it is actually paying a cost. So if you side with, if this is person A and then person B, and this is person C, if it goes towards person B, it is making an enemy out of person A. If it goes towards person A, it's making an enemy out of person B. So there is no unique choice with which person C can choose their disposition. So this is called is one type of frustration. The other type is when all of these interaction strengths between the spins are random numbers. So instead of having the same interaction j, 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 for example, if j is 5, instead of having the same interaction between them, they have, suppose, very different things. Suppose this one is still at 5, this one happens to be at 1, this one goes to say -10. So this is what is called disorder in the system, where you have some imperfections in the system or some changes in the system. And what does it give rise to? Remember, earlier we were talking about equilibrium, and there was one equilibrium, a unique state, which was picked out by the equilibrium. In case of frustrated, disordered systems like this, you get what are called multiple equilibrium. So for the previous example, the energy minimization procedure, if I were to plot energy versus configuration, I would get something, okay, which has some fluctuations maybe, but then a very clean dip at something. So over here it is low, the energy is low, over here it is high. So for the pure case, for the not disordered case, you would have a very clean energy surface like this in most situations, where one configuration or some very tiny symmetry related configurations get picked out by the system at low temperatures. In case of classy disordered systems, what you get is something like this. So you have many local minima over here, and you have something called transition states, you have something called an ideal glass state, so on and so forth. So what physically what happens is that earlier, for example, if I go to the early example, the system was supposed sitting somewhere over here at some ambient temperature, which tells you the scale of energy. As the temperature is lowered, the system kind of explores and then falls into this minima over here. And this is the global minima, which means that if it actually tries to escape out of this thing, it goes back again. It's pushed back. It cannot actually escape. The same thing happens over here, but it happens for the local minima. For example, if the system were to start out here, the global minima is somewhere over here for the glassy thing. The actual global minima is here for the crystalline phase, where everything is put into an ordered thing, an ordered repetition of sites. So if when the temperature is lowered, it can actually explore this place and get stuck in this local suboptimal minimum in the energy. And then it takes a lot of time for it to actually realize that, oh, well, there's actually something even lower in energy for me. And it actually takes time for it to hop across this barrier and end up in the ideal situation. So this is the main idea between classes. That is the thing that Parisi also won his Nobel Prize for, the main thing that the Nobel Committee also highlighted in their conversations. And this is the underlying feature behind it, that you have multiple equilibria, you have locally suboptimal places where things can get stuck, and it takes a long time for the system to realize that it is actually suboptimal and go to another optimal thing. Now, this thing for multiple people can recall different kind of things, and that is you're very right if you actually are having this feeling. This figure is from this reference. You actually have, so this is from Professor Parisi's Nobel lecture, where you have this landscape, the same landscape that I drew in a very simplified way, actually in 3D looks very corrugated and very complicated like this. So these red lines represent where the object started from and where it can go. So suppose it started from somewhere over here, it can flow down this way or flow down that way, or it can go, try in some situation, try to go up. It can do all sorts. So it can explore the entire thing like this. And this energy landscape that we're talking about need not be just energy. It can be loss for machine learning. It can be cost for optimization problems. It can be risk for financial problems, financial considerations. It can be fitness for some biological algorithm that you're running for something. So already I've told you that this kind of the underlying phenomena is true for multiple different things, from starting from biological biological systems to economic systems, machine learning algorithms, physics, so on and so forth. So this basic idea and the techniques used to solve these ideas are present across the board. Now, let's talk finally in the last maybe 10 minutes that I have, let's actually talk about the hardcore, well, a diluted version of the hardcore stuff that Parisi actually has done. Remember, Professor Parisi is a theoretical physicist, and his research has been, for the most part, very mathematical and very difficult to give easy interpretation of. In fact, the technique he used to solve the glass problem, which I'll define in a moment, actually took him quite a while before he got physical understanding of it himself. In his own words, he actually solved the problem first, then stared at it, and then later on, at least 3 years after he actually found the solution, he found the actual underlying physics behind it. So with that little intro, or rather disclaimer, let's talk about glasses. So ideally, glass really surrounds us. I mean, it's there in our windows, it's there in your glass from which you drink from. Ideally, the window panes, the glass, you would imagine to look like this, right? I mean, you hope that it looks like this. Ideally, it doesn't, unfortunately for us. But what I'm trying to say is that if you try to look outside, you should have an unrestricted, clear view if your glass is clean, that is. However, for old windows, you see that over time, the glass sort of distorts or gets distorted in different places. So even if you had a clean image earlier, after say 50 or 100 years, this is true, is very much seen in old cathedrals around across Europe and so on and so forth, where glass sort of changes over time, over a really long period of time, centuries in fact, but it changes over time. So what is actually happening? So this has something to do with the actual underlying arrangement of them. So for quartz, all the silicon, so glass is made of silicon oxide. The silicon and oxide atoms in quartz, which is one of the phases of glass, actually are in regular nice patterns like this. This is called a lattice, a proper lattice. Whereas for glass, they are very disordered. They're randomly connected to each other. There is no homogeneity between one sector and another. So this is the disorder in a glass, which also makes it get trapped in some suboptimal minimum of configuration. And over time, it realizes that it is suboptimal and shifts to something more optimal. That's why you get these distortions in the glass. Now, what does it have to do with Professor Parisi's work? Professor Parisi actually contributed to things called spin glasses. So spin glasses are basically some kind of an alloy. So usually it is full of copper with some very trace amount of iron dispersed inside the lattice. This illustration is from the Nobel outreach document that was circulated. Now, usually if you just count, so iron is magnetic, it has these little arrows pointing one direction or the other. However, within this spin glass phase, the iron atoms get frustrated. They don't know which direction to collectively point in. And you would expect that, well, okay, if they're in random directions, overall, their total direction should be 0. So for each, if they're completely random, each direction in one way would probably have a partner which is pointed in the other direction. They cancel out and I should get 0. Turns out this is not the case. This material, this alloy actually has a stable magnetic phase, which is actually shown in this material over here. So at a certain temperature, which is over here, the magnetization varies in this way. Below that temperature, depending how it is approached, whether it's approached from this way or whether it's approached from this way, it is actually following, if it is actually showing different magnetizations at different places. So this particular curve is from Professor Parisi's work as well. So this is an actual experimental measurement on a system like this. I don't remember exactly which system it was. And the above is some theoretical prediction from Professor Parisi own work, which actually replicates the qualitative behavior that it's different when approached from different directions and has this kind of behavior. So how did Professor Parisi actually figure this out? So this is something called the replica technique, which Professor Parisi actually found interesting ways to, or rather insightful ways on how to exploit. So earlier, as I was saying in this example as well, and I'm going to switch the colors. So suppose the red ones are all copper atoms and the green ones are iron atoms. So in one particular case, say the iron atoms are all distributed like this, some random way. In some other realization of the sample, or in some other macroscopic area of the sample, the iron atoms would look like this. So each one of these is like a configuration. So this is, say, configuration 1. This is configuration 2. Remember, since the sample is really large, the configurations can actually happen in macroscopic areas in the same sample. And this is going to be important for later on. Now, these configurations can happen, and then what you would like to do is to average over all of these configurations for each sample. What Professor Parisi realized is that to calculate the thermodynamics of this object, to minimize the energy, you have to replicate this system into multiple copies. So this configuration would be part of some particular copy called a replica. So this would actually gain a replica index as well. So some replica labeled alpha, this will be some replica labeled beta. And based on this, you can actually get some order parameter in this, meaning that you can get something which actually looks at what is going to change or what is going to tell you. For example, in the magnetic case, it was the magnetization, which was 1 in one phase and 0 in the other phase. In this case, the order parameter turns out to be the overlap. So to define it, the overlap is just the same spin, the average of the same spin between two different replicas, averaged over all configurations of disorder. And this is called Q alpha beta. Now, since their disorder average means that in configuration 1 as well, I basically average over all possible disorder. On this configuration as well, I average over all possible disorder. In that case, there is no a priori reason for me to expect that one replica is different from the other replica. On average, they should be the same. So in general, when I do all of this, both of these things should be the same, and Q alpha beta should have a same value for if there is what is called replica symmetry. So they should have the same value of Q. So this is replica symmetry. So what that means is that all of the replicas are the same on average. I don't, there is no means for me to distinguish between these two things, but, and that's why this Q alpha beta order parameter, which is called the overlap, should give me the same thing. However, what Professor Parisi realized is that if you group these replicas in some particular way and try to extract their behavior of this overlap functions, you get something called replica symmetry breaking. So what is basically happening is this Q alpha beta, which was equal to Q in the symmetric phase, now actually depends on alpha beta. So that is not equal to Q for all, for all alpha and beta, meaning that this overlap is different for different replicas. So overlap is different for different replicas, right? So what that happens, the replica symmetry is broken, and this is the physical mechanism through which you expect this glass transition to happen. Now, going back to susceptibilities, what actually happens, so this replica symmetry is broken below some temperature. This is the T is called the glass temperature over here, right? So over here, for example, the glass temperature is somewhere over here. This is Tg. So on this phase, the system can actually explore all of the configurations available to it, and you get a collective response. The replica symmetry is not broken. And on this side, replica symmetry is broken. Symmetry broken. What that means ultimately is that, as I was saying, in this phase on the right side, the particle can hop between all of these things and figure out things. In the other situation, the particle is more lethargic. It gets stuck in some minima like this and stays there. So what you're seeing on this side is some local response, which is guided by the local fluctuations. On the other hand, it is something from the total material. So that is all that I had to say about magnetization. And since I'm out of time, let me just flash this particular slide from Professor Parisi's talk at ICTS. So this is a slide of all the people that he has worked with. The size is proportional to the name. The size of the name is roughly proportional to the number of papers that he has with them. So I find this is a very pretty slide, very interesting and curious. You see a lot of large names in the field in there as well. And with that, I also thank you for your attention.
Thanks. That was a very nice explanation of all the work that Parisi has done, or at least some of the work that Parisi has done.
Some, not all.
Not all would be impossible.
All is too much.
And thank you for taking the time to start from the very basics and try to explain things. Okay, so let's see if there are questions. I see there are some questions on the chat. So let me just see. These are questions that have been plugged in here, but let me ask Dinesh if he has any question. I can even allow him to talk if he wants to ask a question in the audience. And okay, there are a couple of questions. Dinesh, do you have a question? If you are, please.
I'm just trying to process everything. It's very fascinating to hear you explain it so well, and the kind of implication it has across multiple complex systems is quite phenomenal. I just wanted to ask, while you've spoken a lot about physical systems,
yes,
in a way, human population also behaves like a complex system. I mean, you all have individual local maxima, and they kind of have an emergent property of a mass which is different. Has anybody even tried to connect this work with anything like that, or that's still sociological work and not something that is right in the realm of physics and biology yet?
No, well, the realm of complex systems is interdisciplinary. So for human actors, it depends on what question you're asking of them. So for example, there have been so there have been models where people try to study voting. So there are models in statistical physics called voter models. There are all of these. Yes.
That's great. I didn't know that. That's
really fascinating. So there are some other examples as well. So there is game theory, for example, is something more aligned to what you're asking for. So this is in the realm of economics, economic considerations. For example, you want to have a resource which is getting optimized, and you want to figure out whether people can optimize between different actors. So there is something called minority games, which I probably won't have time to exactly discuss, but this is related to, for example, the game theory that was introduced by John Nash as well, the Nash equilibrium. So there are examples. I don't, of course, I'm not very aware of what is the state of these things, but I do know that there are examples, and people actually figure out. For example, the Nash equilibrium is the basic idea where when people don't trust each other, they don't want to collaborate, they get stuck in a suboptimal minimum. Whereas when they do cooperate, they could actually get better gains for everybody involved. So that would be one place to start looking if you would like to see.
If I can look at one of the questions in the chat, which is probably related. So, you know, has anybody used this kind of modeling of glasses to model human behaviors?
Human behaviors, I'm not sure. There have been, they probably have. I am not very well aware to actually give you a reference. I did, however, find a paper which was linking glassy behavior, excuse me, that was linking glassy behavior to the neuronal activity in the brain. So you would have, so if I talked about spins being +1 and -1 or 1 and 0, the same kind of dichotomy could be mapped onto neurons, for example. So 1 would be neuron firing, -1 would be neuron not firing. And they can actually find some glassy phases in this simplistic model of neuronal activity, and they could actually link it to memory and how memory is stored, stuff like that. If you want, I can find the reference and give it to you as well.
Interesting, interesting. Okay, there is another sort of, this is probably a technical question. This, you said this replica symmetry breaking happens at a certain temperature.
Yes.
Does this temperature vary for different systems, or are there also some sort of universal things in this? At what temperature does a system transition?
Usually, so the correct statement would be the replica symmetry is broken below below the transition temperature Tg. Usually for all kind of transitions that people have seen, even equilibrium transitions which have nothing to do with disorder, etc., the transition temperature is usually material dependent. The behavior around the transition temperature, in the sense that how fast is the replica symmetry being broken, how different is this Q alpha beta becoming for different alpha beta, that is universal, and that gives the rise to the concept of universality, which means that the same kind of physics can explain say magnets, Ising magnets particularly, and say the phase transition in water. So yes, the temperature does usually vary with different systems. And I see, this is Manisha's question, replica symmetry break at a particular temperature. It breaks below, at and below the temperature, and breaks because the temperature is so low that it doesn't give the particle enough energy to explore the complex energy landscape that it has. It just gets stuck at a minimum. It doesn't have enough energy to pull itself out. That is the simplistic idea.
Okay, and finally, there's another question. Is it possible to define a degree of complexity of a given problem?
So it is, so a priori you could say that, well, a degree of complexity would be related to how many possible choices you have given your constraints. So remember when I talked about frustration, maybe I can go to this slide. So wait, I forgot where this slide is. Spin glasses, no. Well, regardless, I can just draw it over here. So suppose you have a spin pointing up and a spin pointing down. Remember, I told you that if all of them want to anti-align, the third one, the poor guy doesn't know which way it would go, either this to minimize its bond with this guy, or whether it would go this way to minimize its bond with that guy. So in such a situation, there are two possible states, and actually much more than two possible configurations of classical situations which can happen. So you can define the degree of complexity by these possible number of states. The large, so this is for only 3 spins. In a realistic system, you would have a much larger array of things, and you would have frustration in the entire thing. So in a sense, they would have some entropy as well. So maybe you can say you can define complexity by this. There is a technical answer to this question as well, which I am not very well versed with, which relates to the exact answer of why these glasses are stable. There is this concept called ultrametricity, which I wouldn't have the time to actually touch upon, which basically tells you that distance between 2 configurations is distance between some very complicated hierarchical structure, like a network. For example, one configuration, remember the classical complex systems diagram that I drew for you? So each configuration gets grouped into certain larger groups, which then get grouped into certain larger groups, and then so on and so forth. So they have some tree-like, network-like structure. So this is, say, configuration 1, configuration 2, 3, 4. So if I had to hop from configuration 3 to configuration 4, I would actually have to go 2 levels up and then come down. And these levels are effectively arranged according to complexity. So this is a hand-waving heuristic answer, but then there is a, as I said, this is a technical answer to your question. This also is there.
Okay, good. So, all right, if there are no more questions, let me just quickly check YouTube once. I don't think there are any questions there. So if there are no more questions, let us thank Saranyo once again for this brilliant tour through the works, some of the works of Parisi. Thank you so much for taking us through this. And let me remind you again that next Sunday, 26th, we will have a special chaiandwhy session to look at the other half of the physics prize for climate change, as well as the chemistry prize for asymmetric catalysis. And following that, we'll move into 2022, where hopefully we will be back to our physical sessions, but we will also do the online sessions as well. So stay tuned. Follow us on Twitter and Facebook. It's at chaiandwhy, or send an email to outreach, outreach at tifr.res.in, and we will add you to our mailing list. Stay safe and have the best of the end of the year 2021. Thank you.
Okay.